Hello, I'm Roman, and welcome back to the series of the videos Neural Networks from Scratch in Golang, where we using this book, Neural Networks from Scratch in Python, but writing everything with the Golang. And in the previous episode, I've been implementing new things called L1 and L2 regularization during the model training, and in the end of the video, I started to test it, and it turned out that something went wrong with the implementation, and I supposed to record this video yesterday. So today is the Sunday. I'm usually not recording on the Sundays. I wasn't able to record it tomorrow, but I was very curious what went wrong. So I kind of at least took a look at the code and compared it once again, and turned out that I made a mistake, well, in L2 implementation. And basically I've been changing the debiases directly. I mean, I was not adding, I'm still getting used to the API of the GoNum. And for me, it looks like in my world, it should take one something and just edit, but it's a little bit different. But anyway, I made a mistake. I did not calculate these things in, well, actually it was the error with apply. I applied it directly into the devices, meaning that I was replacing the values instead of adding this difference. So I fixed it, and I briefly took a look at the results. I mean, I run the training, and it looks like that was the whole issue. So if we'll run it right now, we could see that the accuracy is actually pretty high. But the main difference should be that the accuracy here is 96%, but here the accuracy is 83. So I mean, it's still a bit difference. And the difference is loss is still pretty much big. So I'm not sure how it's supposed to improve things, but let's take a look. So this is the whole code up to now on the Python, and this is the result that they have in the book. Okay, I made another run, so loss is 0.2. Here the loss is 0.7, so it's still pretty high, I think. But I need to check if I'm actually calling. I'm actually setting these values, and it should be for the regularizer, right? So we have the weights and bias change. Okay, so the reg loss, calculation loss, okay, validation. So for example, okay, it's actually, I would say the same. So they have the training accuracy 94%, but the validation accuracy is 83%. And the loss is twice higher for the testing data. So it's kind of same. The animation showed the training data in the background, dim dots, and the validation data in the foreground. After adding the L2 regularization term to the hidden layer, we achieved a lower validation loss. I mean, it's still lower than it used to be, and higher accuracy. We can take a moment and exemplify how a simple increase in data for training can make a difference. If we grow from 100 samples to 1000, let's take a look. Why not? I mean, let's test. That's we're changing the training data. It became to train much slower. You can see the difference. It's actually gonna take a while. Yeah, but we'll run the concept for the code. So for example, here they have the accuracy is 98%, and their accuracy on the validation is 87%. So, and the loss is very close. I mean, comparing to the previous one. So what we have the loss 0.33. Here I have the loss is 0.39. Accuracy is, well, I would say 86%. And here accuracy 88. So it's so it's pretty close. I mean, it's actually like this. They have difference in around 2% in the accuracy, and I have kind of the same. We can see that this change alone had a considerable impact on both validation accuracy in general, as well as the delta between the validation and the training accuracies. Lower accuracy and higher training loss suggests that the capacity of the model might be too low. Lower accuracy and higher training loss. Lower accuracy and higher training loss. Okay. Suggests that the capacity of the model might be too low. So we need to increase the number of the neurons. A large delta earlier and a small one now suggests that the model was most likely overfitting previously. In theory, this regularization allows us to create much larger model without fear of overfitting. We can test this by increasing the number of the neurons per layer, going with 124 or 256 neurons per layer help with training accuracy, but not that much with validation accuracy. Okay. This didn't produce much of a change in the result, but raising the number again to 512 did improve validation accuracy and the loss as well. So for example, here the accuracy 91%, validation 92. The validation loss is still higher, but way closer. In this case, we can see that accuracies and losses for in-sample and out-sample data are almost identical. From here, we could add either more layers and neurons or both. Feel free to tinker with this to try to improve it. Next, we're going to cover another regularization methods dropout, and that will be... So, okay, let's try... they were... Instead of 64... let's have it very big. And I think that would take a while to train, right? Oh yeah, much slower. Okay, this will take a while, but take a look. The accuracy on the is already very high. So actually, okay, so it took some time to train it and calculate the difference. So let's take a look. So we have the total loss 0.3 and 0.38 on the testing data. Accuracy is 88% when the accuracy on the training data is 90%. So I mean, I wouldn't say that this makes it much, makes the difference much smaller. But again, probably the issue is with the, well, not the issue. I think if I'll run it once again, I will see better results from time to time because the I have weights and biases randomly initialized, and sometimes it make it better, sometimes it make it worse, but it is what it is. Okay, but I think right now I'm done with this chapter L1 and L2. Interesting that we didn't use the L1 regularization. I mean, probably we can try to do this too. But yeah, let's take a look at what is the next chapter bring us. The only thing I want to check is what they have for the chapter code 4, page 300 with missing N. Okay, updated grain dense layer was 2 input features. Yeah, this is what I saw. They clearly had a mistake here with 3 output values, but I mean, it's not a big deal. Okay, let's go to the next chapter. The next chapter is called Dropout, and I want to notice for myself that I officially crossed the 50% of the book. Well, right now it's clear. So, but I think I'm I have enough material to record for the next 30 something videos. And actually, I'm still thinking what to do next after this. I mean, what to do with this kind of framework that we'll get in the end. I have a couple of ideas, but I think I will understand it better closer to the end of this book. Chapter 15, Dropout. Another option for neural network regularization is adding a dropout layer. This type of layer disables some neurons while the others pass through unchanged. The idea, similar to regularization, is to prevent a neural network from becoming too dependent on any neuron, or for any neuron to be relied upon entirely in a specific instance. Another problem Dropout can help with is co-adoption, which happens when neurons depend on the output values of other neurons and do not learn the underlying function on their own. So, it's like when you don't want to learn new material and you rather want to steal somebody's results during the class test. How it's called in English when you're in a school and you need to write some examination, like intermediate ones. Not sure. Dropout can also help with the noise and other perturbations in the training data, as more neurons working together mean that the model can learn more complex functions. The dropout function works by randomly disabling neurons at a given rate during every forward path. Randomly disabling neuron, interesting. Forcing the neuron to learn how to make accurate predictions with only a random part of the neurons remaining. Dropout forces the model to use more neurons for the same purpose, resulting in higher chance of learning the underlying function that describes data. For example, if we disable one half of the neurons during the current step and the other half during the next step, we are forcing more neurons to run data, as only a part of them sees the data and gets updates in a given pass. This alternating halves of the neuron are an example, and in reality, we're using a hyperparameter to inform a dropout layer of the number of neurons to disable randomly. Also, since active neurons are changing, dropout helps prevent overfitting, as the model can use specific neurons to memorize certain example. But I mean, I can see it in the way that this knowledge, first it forces the neural network to learn the rules rather than the memorizing the data. And second, it kind of duplicated. So half of the knowledge is kind of duplicated across different neurons and more distributed. Not sure if it makes sense. This alternate has and the reality with okay. It also worth mentioning that the dropout layer doesn't truly disable neurons, but instead zeros their outputs. In other words, dropout does not decrease the number of neurons used, nor does it make the training process twice as fast when half neurons are disabled. Interesting how the backward path in this case. Interesting how the backward path in this case will change, and I guess we'll need to remember what neurons were disabled during the forward path, so we can ignore this during the backward path. I think that's something like this. In the code, we'll turn off neurons with a filter that is an array with the same shape as the layer output, but filled with numbers drawn from a Bernoulli distribution. Bernoulli distribution is a binary or discrete probability distribution where we can get a value of 1 with a probability of p and the value of 0 with the probability of q. Let's take some random value from this distribution r. So p r equals to 1 equals to p. Let's take some random value from this distribution. What this means is that the probability of this value being 1, the probability of it being 0 is q, equals to 1 minus p. Therefore, This means that the given R value is an equivalent of a value from the Bernoulli distribution with a probability. This means that the given Re is an equivalent of a value from the Bernoulli distribution with a probability P for this value to be 1. If R is a single value from this distribution, a draw from this distribution reshaped to match of the shape of the layer outputs can be used as a mask to this output. We are returned an array filled with values of 1 with the probability of P and otherwise values of 0. Then we apply this filter to the output layer we want to edit. I still don't get where we get the probability. I mean, are we using the layer's output as a probability, or I mean, where we get it, or just random? About 0, about 1.5. I'll just randomly check it. I mean, I understand that the scale of the dropout. So it means that we drop in 90% of the neural networks, of neurons. Well, of the hidden layers, actually. Still don't get where we get the probabilities. With the code, we have one hyperparameter for dropout layer. This is the value for the percentage of the neurons to disable in that layer. For example, if you choose 10% for the dropout parameter, 10% of the neurons will be disabled at random. Oh, okay, so it's random during each forward burst. Before we use NumPy, we'll demonstrate this with the example in pure Python. Interesting that now in the beginning of the book, most of the codes were using the NumPy straight. At least this was my impression. But right now I see more examples with the pure Python. But so we have the dropout rate, we have the example output for the layer. I think for one input, example element contain 10 values. Repeat as long as necessary. Randomly choose index and set value to 0. And for how long? Index random init. Okay. We might set an index that already is 0. There are different ways of overcoming this problem. For simplicity, we count values that are exactly 0. While it's extremely rare in the real model that weights are exactly 0, this is not the best method for sure. Okay, so we will, I mean, in the worst case scenario, we can, like with this implementation, we can get a situation where the random index will return the same index over and over, and we won't go further with this algorithm. But once, if required number of outputs is 0, leave the loop. So yeah, we're just checking the number of the percentage of the dropout values. If it's bigger than the dropout rate, then we're good. And for example, here we have some 50%, so we should have 1, 2, 3, 4, 5. 5. This code is relatively rudimentary, but the idea is to keep 0 neuron outputs, setting them to 0 randomly until we have disabled whatever target percent of the neurons we require. If we consider a Bernoulli distribution as a special case of binomial distribution with n equal to 1 and look at the list of available methods in NumPy, it turns out that there is a much cleaner way to do this using NumPy, random binomial. A binomial distribution differs from Bernoulli distribution in one way, as it has the parameter n, which is the number of concurrent experiments instead of just one, and returns the number of successes from the n experiments. Impeded random.binomial works by taking the already discussed parameter n, the number of experiments, and p, probability of true value of the experiment, as well as the additional parameter size. Okay. The function itself can be thought of like a coin toss, where the result will be 0 or 1. The n is how many tosses of the coin you want to do. The p is the probability for the toss result to be a 1. The overall result is the sum of all toss. Why do I need? The size is how many of these tests to run, and the return is a list of overall results. For example, so we have 2 experiments. I get to just 2 values, 50% and size 10. This will produce an array that is of size 10, with each element will be the sum of 2 coin tosses. It's actually how many times. With the probability of 1 will be 50%. We can use this to create our dropout layer. Our goal here is to create a filter where the intended dropout percentage is represented as 0, with everything else as 1. For example, let's say we have a dropout layer that will add after a layer that consists of 5 neurons, and we wish to have 20% dropout. An example of a dropout layer might look like this. So from 5 elements, we have only 1 missing, which is 20%. As you can see, this is an example of the filter we're going to apply to the output of the dense layer. If we multiply the neural network's layer output by this, we could be effectively disabling the neuron at the same index as 0. We can mimic that with binomial by doing this. We have the dropout rate, we have the something like this. This is based on probabilities, so there will be times when it does not look like the above the rate. There could be times no neurons 0 out or all neurons 0 out. On average, these random draws will tend toward the probability we desire. Also, this was an example using a very small layer. On a realistically sized layer, you should find the probability more consistently matches your intended value. So the bigger layer will be the more consistent it will work. Assuming neural network's output is this, for example, we have this one. Next, let's assume our target dropout is 30%. We apply a dropout layer. So we have the dropout, we have the example, and then we calculate, and then we multiply it by array of ones and zeros. And suddenly we have some of them as 0. Note that our dropout rate is the ratio of neurons we intend to disable. Sometimes implementation of the dropout will include a rate parameter that instead means the fraction of the neurons you want to keep. At the time of writing this, the dropout parameter in deep learning frameworks like TensorFlow or Keras represent the neurons you intend to disable. On the other hand, the dropout parameter in the PyTorch and the original paper on dropout signals the ratio of the neurons you want to keep. The way it's implemented is not important, but it's important that you know which method you are using. Yeah. So the idea that we just want to disable some of the neurons. While dropout helps a neural network generalize and is helpful for training, it's not something we want to utilize when predicting. That's true. So we need it only for the model training, but I guess we'll need to dropout rate once we finish with the model training and we want to call a forward pass. Probably. It's not as simple as only omitting it, because the magnitude of inputs to the next neuron can be dramatically different. If you have dropout of the 50%, for example, this would suggest that on average your inputs in the next layer, neurons will be 50% smaller once summed, assuming they are fully connected. What that means is that we use dropout during training, and in this example, a random 50% of the neuron output of the value 0 at each of this step. Neurons in the next layer multiply inputs by weights, sum them, and receive values of 0 for the half of their inputs. If we don't use dropout during prediction, all neurons will output their values, and this state won't match the state seen during training. Since the sum will be drastically about twice as big. To handle this during the prediction, we might multiply all of the outputs by the dropout fraction, but that's at another step for the forward pass, and there is a better way to achieve this. Instead, we want to scale the data back up after dropout during the training phase to mimic the mean of the sum when all of the neurons output their values. We want to scale the data back up after a dropout during the training phase. So for example, we're dropping 50% of the data, but then we're using a sum and we can double the values. I guess that's the idea. Well, in case, for example, in 30% of the dropout, that will be division by 0.7, and with the 50%, it's the overall race will be bigger. Notice that we added the division of the dropouts result by the drop-in rate. Since this rate is a fraction, it makes the resultant values larger according to the value lost because of the fraction of the neuron outputs being zeroed out. This way, we don't worry about the prediction and can simply omit the dropout during the prediction. In any specific case, you'll find that scaling doesn't equal the same sum as before because we're randomly dropping neurons. So I mean, it's interesting because probably it won't be the same, magnitude of the values. That said, after enough sample, the scaling will average out overall. To prove this, we have a dropout rate, we have an example output, we have the initial sum of the outputs, then for sums, okay. So that's the average of the sum after 10k of the iterations. Okay. Yeah, I think, well, the backward path will be an interesting thing to implement here. The last missing piece is to implement dropout as a layer in a backward path method. As before, we need to calculate the partial derivative of the dropout operation. When the value of the element r equals to 1, its function and derivative becomes the neuron's output. Z compensated for the loss value by 1 minus q, where q is a dropout rate as we described. So we have the function that has neurons output, and it's not a dropout rate, I would say it's keeping rate. So then you calculate the derivative against z, and this part is 1 divided with the 1 minus q is a constant, and then you have only dz over dz again. So it ends up with derivative equal to 1 divided by 1 minus q. That's because the derivative with respect to z of that is 1, and we treat the rest as a constant. So for the r equals to 0, that's because we are zeroing this element for the dropout filter and the derivative of any const. Oh, okay, so that's just another example. So that was for r equal to 1, and this one for the r equal to 0. Then, yeah, then it makes sense because that will be a 0 value and derivative from the 0 is 0. Okay, so right now we have two. We have layers output divided by 1 minus dropout rate, or something that was for the neurons that are left in the calculation, and 0 for the disabled neurons, right? Oh no, this is the function itself. Then we have, okay, how it ended up with R here. Oh, okay, okay, yes. I denounce the index of the given input and the layer output. When we write the derivative of the dropout function this way, we can simplify it to a value from the Bernoulli distribution divided by 1 minus dropout rate, which is identical to our scaled mask. The function the dropout applies during the forward pass, and it's also either 1 divided by negative, no, 1 minus dropout rate or 0. Those we can save this mask during the forward pass and use it with the chain rule as the gradient of the function. So then we have the code, we have the dropout rate or dropout layer. So we store the rate, we take the inputs, we calculate the binary mask, apply mask to the output, but it should be two-dimensional, right? And the backward paths, gradient on the values, we just take the input t values from the from the previous layer and multiply it once again for the binary mask. That should be simple. The only interesting thing is to implement this one. And I'm not sure that the GoNum has something like this, right? So this is what we have. Draw sample of the size int or tuple of ints, optional, output shade, if the given shape is, for example, and multiply it by nk. If the size is known, a single value is returned. If np equals cars, otherwise np broadcast samples are drawn. Okay. So, I mean, here it will mean, that I think it will return distribution. I mean, it will calculate the binomial distribution across, not across the whole array, but it should implement it across kind of separately for each row, because with the inputs we have the number of the samples. I mean, for example, like 1,000 samples, and we want to have this dropout applying for a concrete sample path. At least this is what I understand. The probability density of the binomial distribution is this one, where n is the number of the trials, p is the probability of success, and n is the number of successes. Okay. When estimating the standard error of the probability in population by using a random sample, the normal distribution works well unless production less than 5, where p the population proportion estimate and number of samples, in which case the binomial is used. Okay. For example, a sample of 15 people shows 4 who are left-handed and 11 who are right-handed. Then, okay, so the binomial distribution should be used in this case. So those are the examples. We have all the references, binomial distribution. So then the question, like with a NumPy, it's already implemented, and I will have two choices. First, I can implement the code that was presented like with the pure Python function that will randomly go over the index, over the values and trying to zero them row by row, then calculating the dropout. Well, take the row, try to zero some of the values until we reach a concrete dropout rate, then go to the next one, But I think that will be very slow. The second, well, actually, there are two other options. The second option is to try the binomial distribution already implemented in the Go. And I don't know, maybe actually the Go num has it. Let's quickly take a look. Turns out it is. So I don't actually have the third option. I don't need to use it. I mean, the third option will be to implement this. But binomial implements the binomial distribution, discrete probability distribution that expresses the probability of a given number of successful Bernoulli trials. Okay, so this is what I need. I think computes the value of the cumulative log, but I need one that returns an array, right? Rand returns a random sample drawn the distribution. Okay, then the question if there is something implemented already. What I want to find is the function that will return something like NumPy version, so it will return me an array. If not, then I will just need to implement it using the... I'm thinking probably I will need to create a new dimension, well, mat dense, but then I still will have to go over each row and apply and calculate the binomial distribution. Maybe I don't need, maybe I can do it for the whole array, but I need to check. So the idea that I need to use this binomial, I can use this binomial function. Actually, it's actually different. Interesting that it's different. Binomial returns the binomial coefficient, also commonly referred. Oh, so that's the coefficient, but what I will need to use is this one, right? Rand returns a random sample drawn from the distribution, and it from the binomial numeric receives the, and that I have the n is a total number of the Bernoulli trials and must be greater than 0. We will have 1. P is the probability of success in a given trial. P must be between 0 and 1. And source, which is the rand source, whatever that means. New source. Okay, so this is how I'm going to use it. I will create the new randomization source. I will create the binomial struct with what I have. 1 as n and setting the dropout rate. And then I will... Yeah, so then I will just make a copy of the inputs and apply... Where it is? Not this one. And then apply... Where is it? Rand. And I will apply calling of this method for every element in the copy of the array, and it should return me the correct mask for my keys. That should work. Okay, so this is what we're going to implement in the next video. And probably that will be the end of this chapter, right? So this is the code. Yeah, I think it started to get quicker just because it lists all of the code and I just scroll it, very fast. Yeah, so this is what we're going to implement. Try it out, see if it works, and it should be enough for the next video. Okay, thank you for watching, and I see you tomorrow. Bye bye.